Ever wonder how physicists can predict, like, exactly where a satellite is going to be, or how long it'll take for a car to stop? Well, it's not magic. It's all about a few incredibly powerful rules called the equations of motion. So let's dive in and see how they let us map out the entire world in motion.
Right, think about a car driving down the road. It speeds up to merge, cruises along, then slows down for traffic. Every single one of those moves can be perfectly described and predicted with physics. So what's really going on under the hood, so to speak, when you put your foot on the gas? That's exactly the question we're going to break down.
Okay, so before we can jump into the cool equations, we all need to be speaking the same language. Motion has its own vocabulary, and getting these basic terms down is, without a doubt, the most important first step.
First up, displacement. Now this is not just how far you've gone, it's a bit more clever than that. Imagine you walk in a big circle and end up right back where you started. Your total distance might be a mile, but your displacement? It's 0. That's because it's just the straight line distance from your starting point to your final one. Simple as that.
Okay, next we've got velocity. This is all about how quickly your displacement is changing over time. And here's the really crucial difference from just speed. Velocity always has a direction. So a car going 60 miles an hour north has a totally different velocity than one going 60 miles an hour south. The formula is simple, just displacement divided by time. It tells you not just how fast you're going, but, just as importantly, where you're headed.
And that brings us to the big one, acceleration. And listen, this isn't just about speeding up. It's any change in velocity. So yeah, speeding up is acceleration, but so is slowing down. Even just turning a corner at a constant speed is a type of acceleration, because your direction, and therefore your velocity, is changing. We figure it out by taking the change in velocity, that's your final velocity v minus your initial u, and dividing it by time. That unit, meters per second squared, might sound weird, but all it means is how much your velocity changes every single second.
All right, definitions are great and all, but let's be honest. Sometimes a picture is worth 1,000 words. So let's see what all these ideas actually look like when we put them on a graph. It really makes things click.
Okay, check out these two graphs. They both show displacement versus time. See the one on the left with the flat horizontal line? That means displacement isn't changing at all. The object is just sitting there completely still. But now look at the one on the right. That straight diagonal line tells us the object is covering the exact same amount of distance in every second. That right there is constant velocity. And the steeper that slope, the faster it's going.
Now this is where it gets really interesting. Let's look at the same kinds of movement, but this time on a speed-time graph. Suddenly, that flat line on the left doesn't mean at rest anymore. Now it means you're moving at a constant speed. And the sloped line on the right? That's our old friend acceleration. A straight line climbing up like that means your speed is increasing at a perfectly steady rate. That's constant acceleration.
So, what does acceleration look like if we go back to our first type of graph, the displacement time one? Well, it looks like this, a curve. See how the line gets steeper and steeper? That's telling you the object is covering more and more ground in each bit of time. It's picking up speed. This curve is the unmistakable visual signature of acceleration.
All right, we've got the vocabulary down and we've seen the pictures. It's time. Let's open up the Physicist Toolkit and look at the actual equations that tie all of this together.
These 5 little symbols are basically the building blocks for everything. We've got u for the velocity you start with, and v for the velocity you end with. Then there's a for acceleration, t for time, and s for displacement. Just about any problem we want to solve is going to involve some mix of these 5 things.
And here they are, the 3 main equations of motion, at least for constant acceleration. These beautiful, elegant formulas are what connect all those variables we just talked about. I mean, think about it. With just these 3 equations, if you know any 3 pieces of the motion puzzle, you can almost always figure out the other 2. This is the absolute core of a physicist's toolkit.
Okay, so theory's one thing, right? The real magic happens when we actually put these tools to work. So let's take a real-world problem and see these equations in action.
So here's our scenario. We've got a car, and it speeds up from 20 meters per second to 60 meters per second. We also know it takes a full 80 seconds to do that. The question is pretty simple. What was its acceleration?
Tackling any of these physics problems is way easier if you have a game plan. It's always the same 3 steps. First, just list out everything the problem tells you. Second, look at your equations and pick the one that has the stuff you know and the one thing you need to find. And finally, just do the math.
So let's do it. Step 1. What do we know? Well, the initial velocity, u, is 20. The final velocity, v, is 60. And the time,
t is 80 seconds. Easy. Step 2. Which equation do we need? We have u, v, and t, and we're looking for a. The first equation on our list, v equals u plus at, has all 4 of those. It's a perfect fit.
Now for step 3. We just need to get a by itself. With a tiny bit of algebra, we can rearrange the equation to get a equals v minus u with the whole thing divided by t. Now we just pop in our numbers. That's 60 minus 20, all divided by 80. And the answer is 0.5. But 0.5 what? Never forget the units. They're absolutely critical. The answer is 0.5 meters per second squared. And what that means is, for every single second that passed, the car's velocity got faster by half a meter per second. And just like that, we've solved it.
So what this all really shows us is that motion isn't just this random, chaotic thing. It actually follows a hidden set of rules that are totally predictable. Once you learn the language, see the story in the graphs, and know which equation to use, you literally gain the power to describe and predict the journey of any moving object. And that is the foundation for everything from building bridges to sending rockets to Mars.
So we've gotten pretty good at describing motion in a straight line. But what happens when you throw something? You know, like a baseball? It doesn't go straight, it makes that perfect arc. Gravity is pulling it down, introducing a curve into its path. How in the world do we describe that kind of motion? Well, that's a story for another time.